In this lecture, let us look at the spatial specificity of the functional MRI signal. The spatial resolution of fMRI is limited by a number of factors: the technology, the signal-to-noise ratio, or SNR, that is, as the voxels get smaller, the signal-to-noise ratio decreases, and ultimately, the spatial scale of the blood flow changes. One of the limitations in terms of trying to acquire data at higher and higher resolutions is that it takes time to acquire the data at higher resolution. Now, during this time, the signal decays with this T2 star decay. And so even if we were to collect more data out here at longer times, there's no more signal left. So we're not really gaining any more information. However, we can get around this by using parallel imaging. As I discussed in one of my lectures on parallel imaging, by using multiple radio frequency coils, we can get an increase in the signal-to-noise ratio, but we can also use these sensitivity profiles from each of the coils to do some additional spatial encoding. That is, we can skip lines in K-space. The image ends up being sort of wrapped up because of the reduced field of view, but we can unwrap the image because of the different sensitivity profiles from each of the different coil elements. And here's an example of that for functional MRI data from Jeff Dunn and Jerzy Bodurka at the time at the National Institute of Health, showing an fMRI activation map at a pretty good resolution of 1 by 2 by 4 millimeters. Now, as I mentioned, one of the other limitations to the spatial resolution is the signal to noise. That is, as you increase the voxel size, the signal to noise decreases. Certainly, having multiple radio frequency coils can help improve the signal to noise ratio. Another way to improve the signal to noise ratio is by increasing the strength of the magnetic field. Here's an example showing the fMRI signal changes from a 0.5 Tesla to 1.5 Tesla to 3 Tesla. And you can see that the percent signal change during the activation scales linearly with the strength of the magnetic field. And now there are more and more scanners coming out that have strength of highest 7 Tesla and even as high as 9 or 10 Tesla at the University of Minnesota, or 11.7 Tesla at the NIH. Ultimately, the limit to resolution in fMRI is, of course, the blood vessels themselves, because that is what we're imaging. And here's a schematic of that showing the blood vessels penetrating into the brain. So the limit to the spatial resolution really is at how fine of a scale are these the blood flow changes controlled. Well, it turns out we can actually get pretty good resolution with fMRI. Now, if you look at the signal from the left and the right eye in the visual cortex, they're organized in a pattern called ocular dominance columns. These columns are on the order of about 1 millimeter or so apart from one another. And that is what's shown here using an optical imaging technique. It turns out that we can actually measure these ocular dominance columns using fMRI, as shown here in this study from Ravi Menon and Seiji Ogawa. And just to show that this is actually repeatable, this is a further study showing that this particular banding pattern was actually repeatable in a second experiment. So what that says is that even though we are looking at the blood vasculature with fMRI, we can still map functional changes down to below 1 millimeter. And one other important thing to keep in mind is that when we have an activation shown schematically here at the top that occurs in the capillaries, the changes in the blood oxygenation propagate further down that vasculature, down into the venules and the veins. And these might actually be some distance away from the actual